Hello, hello. With this video, we're going to take a look at parametric derivatives. You've been looking at that in terms of graphing parametrics for a while, and now we want to figure out the derivative. I'm hoping what you read about the first derivative made sense, and so this video is going to mainly focus on the second derivative of parametric equations, which is quite a bit more complicated. And to do this, we're going to take a look at both an equation with numbers and then just the symbolic algebraic notation as well. And so I'm going to do that divided up right here in the middle. On the left, we're just going to do the algebraic, and on the right, we'll do some numbers. So a parametric equation means you have an equation for your x and you have an equation for your y. And they're both functions of t. So x is equal to f at t, y can be equal to g at t. And so for some numbers in our example, we're going to use the equation x equals t squared minus 4 and y equals t cubed minus 5t. So first off, the first derivative. The derivative is simply a fancy way of saying slope, change in y over your change in x, which in the case of our parametric functions, hopefully it makes sense that that is y prime over x prime. When we do that with our numbers, the derivative is going to be equal to the derivative of the y, which will be 3t minus 5, over the derivative of x, which is 2t. The first derivative is fairly simple. It's the second derivative where things get a little more complicated. So let's draw a line here, and we will take a look at the second derivative here. And I'll try to label the second derivative. It's a little more complicated, but I think I can make it make sense here. So our second derivative is simply taking the derivative of the first derivative. And so we're taking the derivative again. So the derivative squared of y with respect to x. That's the second derivative, x squared, is simply the derivative with respect to x of our first derivative. Okay? That's all it is. And so with our numbers, we have to take the derivative with respect to x of 3t minus 5 over 2t. Right there. And so that's what we're going to have to do. Now, I'm going to switch over to the numbers here for a second and pay most attention to those. When we take this derivative, I'm hoping you see the problem here. We're taking the derivative with respect to x, but our function in here only has t's. They don't match. And so that means we're going to have to add a chain rule when we take this derivative. We're going to have to add a dt dx. If you remember that from implicit differentiation, you have to add that when your variables don't match. So we're going to take the derivative of the function with respect to t, just like we'd want to, 3t minus 5 over 2t. But then we're going to have to multiply by the derivative of t with respect to x to get us back into the x variables. Now also that presents some problems because when we take the derivative with respect to t, that is going to take a quotient rule. Not exactly pleasant, but it's not exactly hard either. And then we're also going to have to do some fixing with this dt dx, which won't be too difficult, but it is a little complicated. And so I'll talk about that right now, off here to the side. Alright, so dt dx. We don't know what dt dx is, but we do know what dx dt is. That is simply the derivative of x with respect to t, which we know we've done that already. It appears a couple of places in our work. It is right here, or simply x prime over here. Now, sadly, we don't have dx dt, we have dt dx. But if we want the reciprocal, we simply take the reciprocal, and now these two are equal. If we want to flip them, we flip both of them. And so this is now going to replace dt dx, because that is much, much easier to calculate. Alright, so let's keep going with our numbers. We have to do a quotient rule here, so I'm going to do that fairly quickly. The derivative, oops, I forgot a squared in there, didn't I? Let's back up here. Hopefully you saw that as I was going along. The derivative of y is t cubed, so that would be 3t squared, 3t squared, 3t squared. Sorry, I can't go back and remake the video. I don't have the time to do that. Hopefully that didn't confuse you. So, now we're going to take the derivative of the top, which will be 6t, times the derivative of the, or times the bottom, which is 2t, minus the derivative of the bottom, which is 2, times the top, which is 3t squared minus 5, all over the bottom squared, which will be 4t squared, times, don't forget the second part here, we don't want to forget that this dt dx is still here, which we are turning into 1 over dx dt, which I will rewrite as 1 over dx dt is simply x prime. And so as I simplify this, 6t times 2t is 12t squared minus 6t squared plus 10 all over 4t squared times 1 over x prime, which we know over here is 2t. And we can simplify that even further. 12t squared minus 6t squared is 6t squared plus 10 over, multiply the denominators, that will give you 8t to the third. And if you wanted to simplify that even further, you can divide everything by 2 and get 3t squared plus 5 over 4t cubed, which would be our second derivative. Our second derivative right there. Alright, so that's what it looks like in numbers. Now I want to translate that to just variables. So we're taking the derivative with respect to x of our first derivative, but remember the first derivative only had t's in it. And if it only has t's in it, our variables don't match. As you can see, they did not match over here in the numerical example. So in order to do this, it's going to have to become the derivative with respect to t of the first derivative, which I'm going to write, the first derivative is dy over dt over dx over dt. If you remember from the first derivative, it's y prime over x prime from up here. Y prime is dy dt, x prime is dx dt. I know it doesn't fit, I apologize. But because we had to change our variables, we have to add in that dt dx, just like that. And then what we'll do is change this second part, the dt dx. We're going to change that into 1 over dx dt, or 1 over x prime. Can I pause this for a second? Alright, sorry about that. I started to doubt myself. I actually did have it correct. It's not written very pretty, but everything is right. As we're doing our second derivative here, we have the derivative with respect to t of dy dt over dx dt times dt over dx, which we're turning into 1 over x prime, just like what we did before. That means it's going to move into the denominator of all of this, because it's going to be multiplying. Although to write that a little nicer, derivative with respect to t, instead of saying dy dt, I'm just going to say y prime over x prime. Makes it a little bit nicer. And so what you end up getting is, if you want the second derivative, it is the derivative with respect to t of y prime over x prime. And like I said, the x prime over here is moving into the denominator all over x prime. And that there is your second derivative. Now when you actually calculate that, you will often have to do a quotient rule, because this is often a fraction, and that's why you see in our numerical example there was a quotient rule. So you will not get out of using the quotient rule, but that is where the definition from the book for the second derivative comes from. The third derivative is very, very similar to that, but there you have it. Sorry, I had to stop the video right at the end there, but what we had was completely correct. I hope that clears some things up.